Hey, Izzy, you there?
Hi,
Can you
yes,
hear me?
I'm here.
You can hear me?
Yeah, I can.
Awesome. How are you?
I'm good. How are you?
I'm good. I got to work through all those problems, so I'm ready to go. Are you ready?
Yes. I did number 6, but it could be totally wrong. I just tried doing it. That's the
Okay.
only one I can.
Sounds
It's
good.
good.
All right. So, can you see this screen? Do you see this black X I'm drawing right there?
Yes.
Awesome. Cool. All right. So I'll tape this so you could go back and watch it.
Okay.
And I think these are just like extra copies or extra problems I made, but I'll go
Okay.
to, let's see what it was. All right, you want to start at the bottom and move up?
Sure.
Alrighty. So number 10 there, do you see that?
Yes.
You guys are working with the what's called Cavalieres principle or something like that?
Yeah, I talked about it a while ago, but I kind of forgot what
Super,
it means.
super duper easy. You ready?
Yes.
All right, it is about this. It's if you have a rectangle versus pretty much a parallelogram. So here's a rectangle, right?
Mm-hmm.
So that rectangle has a base, like we'll say maybe it's like 12 inches, and then has a height like 7 inches. And remember, your vertical height always has to be that right angle from the base, right?
Yes.
It can't be like any slanted, can't be any slant like that. It's got to be a vertical 90-degree height. So area, you know your area, right? You just times those two.
Yeah.
So that's no problem. And then get my calculator ready for that. If I could find it. So all this principle says is if you get a parallelogram, you're still going to have the same area as long as you got those two bases that are the same. And what I'm trying to do is I'll try to draw a parallelogram best I can like this, like slanted over. And then I saw even more random pictures like this. They had like two bases like this. And then they had curved sections. It was like kind of random. All right, do you see those?
Yes.
All right, so the rule is as long as you have two bases that are the same size and you have from that base, no matter what, a vertical up and down height like this, you see that?
Mm-hmm.
So that would be the height of that parallelogram. Like you wouldn't want to use one of these as the height, obviously, right? Because it's slanted.
Yeah.
But that height right there, even though this is like slanted and doesn't look like a rectangle, you get the exact same area. That's all that rule is. Does that kind of make sense? Where even
Yeah.
something like this, even something curved, the rule is as long as the two base lengths are the same, and as long as from one of those bases you have a straight up and down 90-degree angle height like that, as long as you got that, it doesn't matter what the shape is, the area is always base times height, just like a regular rectangle. Does that kind of make sense? So like even though this red thing is funky looking, just like a rectangle, area is always base times height. So this, I got my two bases, so that qualifies to times the base times the height right there to get my area. That's all that little rule is.
Okay.
And then, but you remember if I give you a rectangle and give you two numbers, you know automatic how to find that area, right?
Yeah.
So it's all area, just area of rectangle is just base times height. But just sometimes you got a parallelogram or some funny looking shape like this, but you still got a base times a height. That's the main rule.
Okay.
Are you okay with that?
Yeah.
So it says you need to draw draw two figures that demonstrate that principle. So, if I was you and you had to draw something like that, that would be you probably drawing two parallelograms. And again, a parallelogram has two bases that are the same length, but are kind of skewed like that. And then you draw your other sides. So that you've seen parallelograms, right?
Yes.
And then you'd have to just say, this is 12 inches. And then this height right here, maybe just make that up to be like 5 inches or something.
Okay.
That's the same as you drawing just a normal rectangle that's 12 by 5. That right there, those two pictures, that's illustrating that principle. As long as you have two bases that are the same length and you have from one of those bases a 90-degree vertical height, then that qualifies. You can multiply those two to get your area. What do you think?
Yeah, I think that seems pretty easy.
So not too bad, right?
Mm-hmm.
Okay, how about number 9, or the scale factor of area and volume? What do you any idea, inkling about that one? Well, solid, just like a solid means, there's area. If I tried to make it, three-dimensional, there's something three-dimensional right there. I'm not very good at drawing. But for this one, if you take a scale factor, scale factor means making something bigger or smaller, right?
Mm-hmm.
If you have a scale factor smaller than 1, it's getting smaller. And if you had a scale factor that represented a fraction like bigger than 1, or like maybe like a whole number, like times a scale factor of 2 or something, those mean you're getting bigger. Do you remember how we did that? I think we did those before, right?
I think we have, yeah.
Okay, but you just got to know in the back of your mind, scale factor, if it's a fraction, you mean it's something shrinking. If it's a scale factor bigger than 1, it's growing. But for this problem right here, it says what happens to the scale factor of the area and what happens to the volume scale factor. So all you need to do is take that scale factor I'm giving you, that fraction, and know that for area, it would be that scale factor squared. And for volume, it would be that exact same scale factor, but not to the second power, it'd be to the third power. So if I did that 3/4 squared, if you times both of those, you get 9/16. If you times 3 of those fractions, 3/4 times 3/4 times 3/4, and you times straight across like you do fractions, you get 27/64. Does that kind of make sense? So area think squared, because remember area of this rectangle, I multiplied a base times a height.
Yeah.
And when you're timesing those, you're timesing an inch times an inch. That's why you get like square inches for area. That's why for scale factor, you take that scale factor and raise it to the second power, because area is always, base times a height, something squared. Does that kind of make sense? But volume, remember volume is like three-dimensional space, like that.
Mm-hmm.
So for volume, you take that same scale factor, but times it by 3, because remember, volume would be not just base times height. Volume is base times height times like another number, remember? Mm-hmm. And that gives you like, let's see if I times that. 12 times 7 times 2. So volume would be what's called a cubic unit, because you're timesing 3 of those units. And volume represents like three-dimensional space on the inside of that box if I was to draw it. So that's why for volume, let's see, scale factor area, scale factor volume is third power because you're timesing 3 of those. Does that kind of make sense? So if I do a square like this, do you see that?
Mm-hmm.
And I threw some numbers on there. Would you know how to find the area of that little square or that rectangle?
Yeah.
What would it be?
12 centimeters squared.
Good job. What if I said, okay, lady, taking that and timesing it by a scale factor of 1/4? How about that? Would you know what to do if I took that area and shrunk it down by a scale factor of 1/4?
I think so.
So for area, remember, you got to take that scale factor and do what with it? Do you remember? The hint.
I square it.
Yep.
Yeah.
So if you take 1/4 squared, do you know what that is?
12 for 16.
Yes, ma'am. So if you were to take that shape, that area 12 centimeters squared, and take that area and shrink it by a scale factor of 1/4, that means what you're really doing is taking that 1/4 and squaring it, and then timesing that number times 12. It's kind of tricky. It's kind of weird. So it's not like for scale factor, if it was just something like some like length like that or something like that, like 10 inches like this, if you multiply that by a scale factor, you know, it either shrinks or it gets longer. But for area, it's special. You can't just times by the scale factor. You gotta do that scale factor to the second power. So that would give you 12/16 for that one.
Mm-hmm.
So if I did that, that would be, let's do that on my calculator. Yeah, 3/4.
Yeah.
So yeah, that would give you 0.75 centimeters square, or 3/4 centimeters square. All right, but yeah, what if I took that same object though, lady, and said for volume, like maybe what if I added volume to it like this, and said this is 6 by 2 by 5 centimeters. How about that? Do you see that?
Mm-hmm.
How would you find the volume of that now that I made it like 3-dimensional? How would you find the volume?
Instead of squaring it like
Yep. So when I squared it, I times the base times the height. When you try to find the volume, what are you timesing? Do you see how I gave you 3 separate measurements there? So for volume, since I made this 3-dimensional,
Mm-hmm.
it would be that 6 times that 2 like you did for area, but then you'd have to times that little 5 I put in there to make it 3-dimensional. So that would give me 6 times 2 times 5. So this example, I'm trying to illustrate this scale factor. That would be 60 centimeters to the 3rd power. Do you see that?
Mm-hmm. Yeah.
So now the trick is, okay, you're shrinking that volume by a scale factor of 1/4. That's the trick. Would you know what to do if I wanted the volume of that scaled down by a factor of 1/4? Because remember, when I wanted the area scaled down by a factor of 1/4, remember I had to take that scale factor and do it to the 2nd power?
Yeah.
So what do you think you got to do with that scale factor number if you're shrinking it for volume?
What if we set it to the 3rd power?
Yes, ma'am. Yep. So before you take that 60, you're not just timesing it by a fourth. That would be like just some straight edge. You have to take that 60 and times it by whatever 1/4 to the third power is. So that's kind of tricky alone because you're timesing 3 of those.
Mm-hmm.
And that gives you 1/64. So technically for volume, you would be timesing that 60 by 1/64. So there's another problem coming on your paper that has you do just this. So if I scale that down, the volume wise, that would scale down way down to like 0.93 centimeters. It's kind of a weird thing. But again, scale factor for area, you take that scale factor number, square it. Scale factor for a cube for volume, you take that square number or that scale factor number and cube it.
Okay.
So for number 9 here, they give you the scale factor 3/4, and they just say, okay, what would the scale factor be for area? And that would be, right, times 3/4 squared. That's the 9/16 answer.
Okay.
And then it says, what about the volume scale factor? That would be that same 3/4, but times to the third power. That's the 27/64 answer.
Okay.
Because I think it's number 6. You did number 6, right?
Yeah, when we went over, I think I might have did it wrong.
All right, let's see how you did. So you found the volume of a pyramid, right?
Yes.
Let's take a picture of this and move it. So on those first 2 that we did, are you okay on those? That property one? Just trying to do a parallelogram. And then the scale factor one, you're okay? All right. So for a pyramid, you found the area of the base, right? I'm gonna try.
Yeah, I think I totally did it wrong.
What was the area of the base?
I was at the question wrong. Yeah, I didn't get it right.
Did you? Can you see this screen here that I'm drawing on?
Yeah, I can.
Okay. So this is a pyramid, an equilateral triangular base. Ooh, that's tricky. So this is what I drew is an equilateral triangle with a square base, but that's not right. So I'm going to try to draw one with a triangular base. So pretty much the rule is you got to find the area, the volume of the area, or let me draw this here. All right, let's get a triangle here. There we go. Try to draw my pyramid best I can. That doesn't look all that great. Let's try to draw maybe another one here. All right. I didn't draw that very good, but I tried to draw it best I could. Maybe, let me try, hold on here. Let me get something real quick. Hold on a second.
Been doing, right? I don't think it's in the folder.
Are you there?
Yeah, I'm here.
All right, you see that picture there?
Yes.
There you go. That's a real triangular pyramid. All right, so let's see. You got equilateral base with a side length of 4, the height of 10. So I'm going to put those numbers on this. So each of those bottom lengths is going to be 4, I guess, because it's equilateral, like that. And then it has a height of 10. if I found that the volume, let me look for a volume of a pyramid formula here.
Mm-hmm.
Here it is. So the volume is the base times the height. Yeah. Let's hold on here. When I was doing this problem today, I thought it was a square one, but now I'm seeing it's not. It's a triangular one, which makes it a little bit harder because you got to find the area of the base, which is a triangle, and then you got to find the height times it. So hold on a second here. Volume of I'm going to show you a formula here.
Okay.
Do you see that screen there with my triangles?
I see the formula you put up and
That
then it's
volume of,
3.
yeah, square root of 3 over 4, a squared times the height. Have you seen that? Have you used that formula before?
I don't think so. We might have. I don't recognize it.
All right. Well, for a pyramid, an equilateral triangular pyramid, like a prism, that's the volume formula. So you're gonna have to plug in those numbers, and then you're gonna have to worry about the scale factor, because this is a scale factor of volume. Do you see that scale factor right there? That 1/2?
Yes.
So do you remember when you're dealing with volume, do you remember what happens to that scale factor? If it's a half, what do you do with it if it's volume? Because that's one of your problems we just did. You got to know.
If that's volume, we'll take 1/2 and you put it to the 3 of the exponent.
Good job. What if it's a scale factor of 1/2 and you're doing area? What would you do? You do 1/2 squared, right? Okay, so for this problem right here, I mean the nitty gritty, this is an equilateral triangular prism, which has you use that formula right there and has you just multiply by 1/2 to the 3rd power right there, I believe. I mean, so I guess that 4 would be the A, and then the height would be the 10. I mean, that's the only thing I could tell you right there. So for volume of a equilateral triangular prism, it's square root of 3, which is super sucky, over 4, times that 4 number, which is one of the lengths, squared, times that height number, which is 10. And then after all that, I gotta then worry about that scale factor and what I do for volume and take it times a 3rd. So it's kind of a tough problem because you gotta get a number and then you gotta times it by 1/2 to the 3rd power. So fortunately, I'll just do it here. So it's square root of 3 times 16 times 10, and that first part's over 4. So that looks like it's 160 times the square root of 3 over 4. So if I use my calculator for that, that would be, let's see. I mean, I'm not sure if you have a calculator that could do square roots, but square root of 3 is, calculator lets me do it, times 160 is 277.1t divided by 4. So that huge mess just gives me the volume of that equilateral triangular prism. I'm just going to round to 2 decimal places. Do you see that number right there?
Yeah.
But now the main gist of it is, what do you do with that scale factor of 1/2? So the trick is, you're not timesing that number by 1/2, right? You're timesing by 1/2 raised to the 3rd power.
Mm-hmm.
So that would be you taking 69.28 and timesing it by, let's see, do you know what 1/2 to the 3rd power is?
Well,
Do you times 3 of those 1/2s?
whatever it is.
Yep, be 1/8. So you'd have to take that volume, 69.2, and times it by 1/8, or that's the same as, 69.28 divided by 8. Technically, that's the same as timesing it by 1/8. So that shrinks down to 8.66 on my calculator. If you're shrinking down the volume by a scale factor of 1/2, because all that shrinks down. But yeah, area takes scale factor, times it by itself squared. If it's volume, you take that scale factor and you times it by itself 3 times. What do you think so far? I mean, that formula,
There's a lot of steps.
I mean, the steps to the formula, it's unfortunate that you don't really remember doing that, but like I said, the main thing is that scale factor. Scale factor, they give it to you. If you're scale factoring for an area, you take that scale factor squared and you times that by whatever area number it is. If you're scaling something up or down for volume wise, you take that scale factor number times itself 3 times and times it by your number. So that's the main thing that we've done so far. That formula stuff for volume of a equilateral triangular prism is just a really yucky formula. I'm not sure why he did that and didn't do like a square rectangular prism. But that problem we just did again was taking that volume number and then knowing what number to times it by. And that one was that volume number times 1/3. So I had to do 1/3 to the 3rd. I don't know, man. That's just tricky, but again, it's for volume, scale factor of 1/3, whatever volume number you get. Like maybe it would have been easier if you had like a nice neat volume, like 40 cubic centimeters. If I was scaling that down by 1/2, you got to remember, don't times 40 by 1/2, or don't divide by 2. It's that 1/2. Dealing with volume, it's that 1/2 to the 3rd power. You're really timesing by 1/8. If I was to give you area of something, again, the main thing I think he's trying to teach you, area, which is a square unit, not a cubic unit. Area, you would take that same scale factor, but not times it by 1/2, not times it by 1/2 to the 3rd power, but you times it by 1/2. You times it by 1/4. So that's the big thing he's trying to get through to you. What to do with your scale factor number. Times it by itself if you're scaling factor in area. Times it by itself 3 times if you're doing scale factor for volume. That's a big thing I got to make sure you understand tonight.
Okay.
Next, there are these problems where you're converting from radians to degrees and degrees to radians. Do you feel strong on those? I mean, we could get back to those. What'd you get for number 7?
Numbers 7, I got 135 degrees.
All right, that's what I got. What did you get for number 7? I guess. This one.
I got 2 pi over 3.
2 pi over 3. For this one, let's see. Maybe I took 210 degrees for this one, and I times that by pi over 180. Is that what you did? Because if they give you radians, yeah, for this one that you took that 3/4 radians and you didn't times by 180 or pi over 180. For this one, you multiply by 180 over pi. So for the next one, I times by pi over 180. So when I did that one, I got 210 pi over 180. And let's see what my calculator reduced down to. 210. Yeah, mine gave me 210 over 180, reduces to 7 over 6 pi. Can you tell me where you got 2 over 3 pi? Can you tell me the work that you did?
Yeah, okay.
What did you do? Yeah, that I just double checked that on my calculator, and I just double checked that on the internet. I typed in, how many radians is 210 degrees, and they got 3.665, which how'd they get 3.66? Yeah, they times 210 times pi over 180. Yeah, I see. Okay. Yeah, I see another site I looked at, and they got 7 pi over 6 too. So I'm feeling pretty confident about that. Maybe did you get 210 over 180 pi? You did? Oh, you just reduced it wrong. Yeah, yeah, you gotta be careful. If you, I'm not sure what calculator you have, but the calculator that we have that you're more than welcome to use, and I'm not sure if you have them at school, but let me try to show you a picture. But the calculators we have, they do fractions and stuff for you. They will reduce fractions. Oh, we'll just move on here. Just make sure you reduce fractions accurately on that one, because you don't want to miss that one because of reducing.
Okay.
All right, how about these ones with the circles 4 and 5? What do you think about those? Can I show you those?
Yes.
Have you done those yet?
I haven't done 4 yet.
Did you try number 5? That wasn't too bad, was it?
I found a place on Amazon. I just didn't really know how to find the area of the sector.
All right, I went to one of the geometry teachers here at lunch, and he was showing me how to do these so I could teach you. Because I just don't teach you stuff. All right, so this one, number 4, they give you this angle in here, that little theta. See that?
Yeah.
They say that angle is 3x minus 3. That's like the algebraic representation of that angle. But do you remember, based on this picture right here, what that 60 tells you? Because you got a circle. I mean, technically, this is a circle with right here in the middle. And I'm giving you this degree. You know what that angle in the middle is, right?
Isn't that the same as the one on the outside?
Exact same, right?
Mm-hmm.
What about this one down here? That's a little bit different. That's where it's not an angle formed by the center of the circle. He told me some word for it. It's some weird word, but it looks a little bit different. It looks kind of like that picture he shows you right there. Do you see that one?
Is there another picture?
Well, you saw that theta was 60 degrees,
Yeah.
right? Equal.
Mm-hmm.
What about alpha? This one right here, this angle down at the bottom. That would be half of 60. There you go. So that would be 30, right?
Yeah.
So for those, you're just pretty much setting up the algebra of the pieces that he's given you, and he's having you just realize what angle you have right there. So if you know that the angle theta in the middle is 60, and you know the algebraic piece is that 3x minus 3, he has you just do algebra like this. 3x minus 3 equals that 60 degrees. You see that? And then you just solve for x. So adding 3, and that gives you 63, and then you divide by 3. And that gives you what x would have to be right there. I think that's 21. So that would be the answer I would have to use for x right there to plug that in to do the math to get 60, because it has to equal 60 degrees, right?
Yeah.
All right, what do you think about that one? And then the other one, the alpha one, you see what he gave you for the algebraic piece for that one, right? For the alpha one, that 2y minus 12.
Mm-hmm.
So that one, you don't set equal to 60, you set equal to 30.
Okay.
And then that's the trick, 30. If you set that equal to 60 or something, it's the middle one equal to 60, but not that little side one. So yeah, that one to solve for y, lady, you're gonna be adding 12 right there, and then dividing by 2. And I think that one is 21 also. Yeah?
Yeah.
What do you think? And then for z, what about that? So with this in the middle right here, this is the radius, right?
Yeah.
So what's the line called when you have a dot exactly in the middle and you draw a line all the way through it? Do you remember what that line's called for a circle?
Isn't that the diameter?
Yes, ma'am. So since this picture is showing the diameter right there, then that top half guaranteed it's got to have to make up half a circle. It's got to make up that 180 degree, right?
Yeah.
So if it's half a circle, 180, and he gives you part of it 60, what would the other part have to be for z to make that equal to 180?
120.
There you go. It would have to be 120. So that one really wasn't too bad, was it?
No.
Just if you didn't remember your algebra, solving for x maybe, or like for that alpha one, if you set that equal to 60 by mistake, you might miss it too. but not too bad, right?
Yeah.
All right, how about the circle one? So the area of a sector, that was some math. Did you do that?
No, I only found the first one.
Because when I did, let's see, arc length, what I did for arc length there, define this MJ, and I'm not sure if you did this, but for a circle all the way around, the diameter, all the way around, is 2 pi r, right? That is all the way around the circle. Diameter. Wait, is that right? Yeah. Wait, what am I doing? Hold on a second. Yeah, diameter is the perimeter of a circle, right? Oh, circumference. So circumference, that's not diameter. Circumference is, that's a C, sorry. Diameter is 2 radiuses. All right, so circumference of the circle. All right, so for this one, he had me find the circumference of the circle first, and then times it by the ratio of that 120 right there. I'm not sure if he did it that way. But that would be, let's see, 2 pi times that radius, which is 8. So the circumference all the way around for this circle with a radius of 8 right here would be 16 pi. That's all the way around the circle. Does that make sense?
Yeah.
So it's different than area, right? Area is pi r squared. All right, but for circumference, it's 2 pi r. All right, so you take that circumference and then you times it by that ratio of 120 over 360 because it's that part of the all the way around circle. So technically you could put that over 1 and probably would have you reduce that 120 over 360. Your calculator in the real world would reduce that. So 120 over 360, that's 1/3. So this ends up being 16 pi times 1/3, which we would write 16 pi over 3. I don't know if you did it like that, or if you got a decimal.
I got the answer. I just did a different one.
What was your answer?
My answer, for the first one, I found when I did that, I got for 16 pi over 3.
You did? What about area? What did you do for area of that?
I only did the first thing. I didn't do the area.
Okay, so area of a circle is pi r squared, right?
Yeah.
So it's the same kind of thing. You find the area of the whole circle using that radius, but then you times it by that same little fraction right there because you're only finding the area of that one piece of the circle. So just like that other one, I found the circumference. I multiplied 2 pi times the radius. For this one, I find the area first, which is pi times 8 squared. So the area of that circle on the inside, which is way different than perimeter circumference on the outside, would be 64 pi. But then times that same fraction, which really is 1/3, but I'll just write it 120 over 360 again, because it's that part of the circle I'm timesing. So 64 pi times 1/3. For this one, that area of that little section in there is 64 pi over 3. For the area. What do you think?
think that makes sense. So,
Can I just throw some problems at you and see how you do?
sure.
Because I'm ready to just make some up for you. Or do you want to look at other those are all the ones that you circle.
Yeah,
Those are the big ones. You circle 4, 5, 6, 9, and 10 on that email that you sent me.
yeah.
So it looked like for number 8, you're okay with the volume of a prism. You got that okay?
Yeah.
What'd you get for number 8?
I got 81 centimeters cubed.
How did you get 81 centimeters cubed?
I did it wrong.
Oh, maybe I did. Let me take a look. I'm gonna take a snapshot of that problem. Because that'll give me a chance to have you practice your scale factor too. Do you see that picture?
Yes.
All right, so when you found the volume, what'd you do? You times those 3 and then you times by a half, is that right? Or what did you do?
I did half. I think what I did is I did half. I think I found like the piece of the found on the triangle, like the area of the triangle, and then I think I did that and multiplied it by like the 9.
Okay. Because it looks like that's like half of a square prism, right? Doesn't it? Kind of? Like a prism that was whole but been cut in half, kind of? I don't know. So I found the volume by multiplying those 3 numbers and then thinking that was half of a prism and times that by 1/2. Is that what you did? Times 3, 6, and 9? Because 3 times 6 times 9 would give you the volume if it was like a square prism. But to me, that definitely is not a square prism. It's not a prism with all 4 sides like this. That to me looks like half a prism, kind of, doesn't it to you?
Yeah.
So I take that volume number and I cut it in half. So 162 divided by 2, I got 81. Is that what you got?
Yeah, that's what I thought.
All right, so did you do that by cutting it in half, or did you use a special formula, or what did you do?
I watched the video on how to do it, and then I kind of like went along with as I worked out the problem.
Okay, well just know for this one, it's you just take those 3 lengths, you times them, but then since it's not a square prism, you don't stop there. You got to take that and cut it in half.
Okay.
But now the question is, all right, lady, what if I was scaling down this volume by a scale of 3/4? What would I times 81 centimeters cubed by to get it scaled down by a factor of 3/4 for volume?
Wait, I'm trying to find the volume.
I'm wanting to take that volume number and scale it down by a factor of 3/4.
Okay.
That's my scale factor. So what am I going to do to that 3/4 before I times it by 81? Yes, ma'am. So now the trick is, what is 3/4 cubed?
I thought 27%.
100%. Good job. So you would take that 81 and you would times it by 27/64. And, you know, I don't know if you have a calculator or not, or if you could figure out what 27 divided by 64 is first, and then times it by 81. I mean, that's really maybe what you need to do. But that 27 over 64 times 81 would reduce that number down to 34.17. And that means if I took that original prism and I shrunk it down, like, do you see this picture here? It's like I'm shrinking it down just like that. So it used to be a big area of 81, but because I'm shrinking it down proportionally with volume, it shrinks down to 34 centimeters cubed for the volume. Where someone by mistake, they would just take that 81 and not take 3/4 to the third power. They would just take 81 times 3/4 by mistake, and they would wonder why they got that wrong. But not you. You're going to take that scale factor, and for volume, you're going to cube it, right?
Yes.
What if I was doing area? What would I do with that scale factor?
Square.
Nice job. All right. Do you want me to throw like one of those circle problems at you? Or do you want to look at another specific problem? Or do you want to practice some more radian problems? How about circle one? Can I throw you a quick circle one?
Sure.
All right. So let's go to blank page here. And then remember, I'll send you a link to this video. You can always go back and look at it at your own speed. All right, so for this made up problem here, I'm going to say this is 80 right here. And I'm going to give you an algebraic piece here. I'm going to say, okay, theta is 2x plus 10. And then alpha is 2y minus 4. Would you know how to solve for x and y there if I threw a problem like that at you?
Yeah.
All right, what would you do?
I'm not sure what it's called at the circle of the line. The one that's in the middle, like that angle. What's your called?
This one right here? Yeah, that's the Greek symbol for theta.
Okay. Well,
And this is the Greek symbol for alpha.
okay.
They use those for angles to try to be all fancy.
So, I didn't see it like a letter there. So
I don't know, just because they're angles. Because they're angles, you don't want to just put X in there, I guess. You got to use fancy Greek letters.
And then for the top one then,
Top one.
it would be English, so then you would 2x plus 10 equals 80. And then just
Good job. And then you would know how to solve that for X, right?
Yeah.
What would you do?
Subtract 10 for both sides.
Good job. And then your final step would be to
Divide by 10 both sides.
all right, no problem. So this one looks like it would be 35.
Yeah.
All right, now the trick, they're having you solve for alpha here using that same 80 degrees. What do you do? What do you got to be careful? There you go, yep. Good job, 40. Yep, half of that 80, right?
Yeah.
Good job, lady. And then that's just adding 4. And then that one looks like y is 22 for that problem I made up. All right, so I don't see that problem being hard for you tomorrow. Just watch your algebra.
Okay.
How about another circle one? How about... Oh, yeah. Sorry. Didn't do that. I forgot that. All right, so if I give you that's 80, what would Z be? There you go. Do you remember, I'm just going to throw a little bit extra at you. Do you remember circles like this, lady? with, you know, all the main properties, right? So if you have an opening in the middle and this is 20 degrees, you know what this length out here is, right? Or what angle that is, right?
Yeah, like the measurement of that.
Yeah, so that would, and then if they started getting fancy in it, do you remember one of these with like the angle on the outside? Do you remember doing one of those?
Yeah, I don't remember doing one of those.
Because he showed me one like this, like if he said this is 70 right here degrees,
Oh,
and this piece is 40. Would you know how to find that little angle right here?
yeah. But that wouldn't be the half, right? It wouldn't be half, like, of 70 because isn't it not at the edge of the circle?
Yep. Yeah, it would have to be at the edge to be the halfy, right? Yeah, this one he's showing me you take that 70 and that 40 and you add them up, and then you divide that by 2, I think. Wait. Sorry. No, I'm sorry. You don't add them, lady. You subtract them. You take that outer angle one, that 70 minus 40, and then you divide that by 2. So that would give you a 30 over 2. That would give you 15.
Oh, okay.
But those are the biggies right there, where you know it's from the inside center where it's equal to the outside, or that little halfy one like this problem where it's from the edge. And then there's that third one. I don't know if that's going to be on your test, but you might want to write that one down just for safekeeping there, I guess.
Okay.
All right, and let me throw another circle one at you. How about one of these right here? And then I'll open it up to you, whatever I can do to help you out. Let's copy this. Do you see that? All right, so instead of this being 120, please. I'm going to say this is 110. And I'm going to say the radius is 6 inches. Would you be able to find the area of this piece right here? And then would you be able to find the length of this outside part? That's what you got to be able to do. So what's easier to you? Do you want to find the area inside first, or do you want to focus on the outside arc length first?
I'll do arc length first.
Okay, so remember that's the way I approached this problem here. I looked at the entire circle all the way around, and then I just focus on just like what part of the circle that really is right there. So that formula for all the way around circumference is pi times the radius times, it's 2 pi r. So memorize that one, right? So what's the circumference of this circle right here if I give you the radius of 6?
It was like 12 pi.
There you go. But now I don't want you to find the entire circumference of that circle. I want you to find just that one little piece from M to J. What would I do? Oops. Put that back, I'm sorry.
So don't you find what only 110 pi. Like now 110 over 360.
There you go. Yep. So what part that angle is of the entire whole? Because the whole thing's 360, right? So you're finding just that one part of 360. So it's that 110 over 360 times 12 pi. And I don't know if you have a calculator that reduces fractions quickly. I mean, my calculator, when I type in 110 and I type in the ABC button and then 360 and hit equal, my calculator, I mean, that one's pretty easy to reduce, but automatically reduces it down as far as it goes. I don't know. You might want to invest in like a Texas TI 30X, and then I would times that by 12 pi. So what part of the circle that 110 is times 12 pi? For me, that gives me 11 times 12. I'm just going to write it like this. I'm going to say 132 pi over 36. How about that? But mainly, does that kind of make sense what we did there?
Yes.
We found the entire circumference first using the radius. And then we made sure we took that degree that we gave you and just did that fraction over 360 times the entire circumference. That gives you just the length of just this piece right here.
Okay.
Are you sure?
Yeah, I'm here.
I mean, are you sure you're okay?
Yeah.
Okay, how about area? Switch gears. What's area of a circle? It's not the circumference problem. It's not 2 pi r. What's area formula? There you go. So memorize that one too. So for this one, that looks like 36 pi, right?
Yeah.
And then times that ratio again. So the degree we give you over 360 times 36 pi. If you were to do my problem I made up. But the math, you're understanding the math, right? I mean, you see where I get this fraction. All right. And then I'm not sure what kind of answers he wants, if he wants an actual decimal answer or if he wants just something like that. I don't know. And then there were other problems. There was like 2 where you had a circle and you had to draw a tangent, secant, chord. I mean, do you feel good with that stuff? Problems 1 and 2 on your worksheet. You okay with those?
I did number 1, but I did number 2 already. Yeah. I was working on this stuff for.
Okay.
Okay.
So it looks like you're okay with finding 3 centers of rotation between points. For a circle, you're okay with adding a tangent through a line, secant, chord, drawing that. You know how to locate the center of a circle using the compass. Do you want me to show you that? Are you using a compass? I mean, the only way you could really locate the center of a circle is by using the compass. Because he said you need to draw. These are chords, right? Chords are from the edge to edge. Is that right?
Yeah.
So he says you need to draw 3 chords and do perpendicular bisectors of them and find out where those perpendicular bisectors meet exactly. So any 3 chords. So there's my 3 chords. And then I guess you are using a compass on the test? I mean, are you doing constructions? You're using compasses? All right, well, if you are, hopefully you can see this. I'll try to illustrate this, but you need to do 3 perpendicular bisectors. So you do that by, you'd have your compass at the very end of your chord and you would stretch it so it's over half the length. And then you draw your arc. Do you see that?
Yeah.
And then you would stay on that same chord but you pick up the pointer and put the tip on the other end. Best I can. And then swing it around, leaving it the same opening, and draw on another arc. And if you use a ruler and draw a line through those, that's one of your perpendicular bisectors, because you got to do it a line through that. And I'm trying to get my ruler here. So you draw a line through where those intersect, those little arcs. And that line that you draw, that's called the perpendicular bisector. You have to do 2 more of those with the other chords.
So you have to repeat that for each of the chords?
Yep. So I'd have to go to the other chord. I mean, that's what he told me, and do the same thing. Oh, it doesn't look like it's gonna let me move this down. See, I moved the size of my compass. That would have been a disaster right there. But yeah, I got to do that 3 separate times, he told me. And then where those 3 lines intersect, that technically is you constructing the exact center of that circle.
Okay, so where the perpendicular lines intersect is where the center.
Yep, where the 3 lines. Because I'd have to do one for the blue line, one for the green line, and then I'd have to do another one for this secant, this chord over here.
Okay.
But it's always the same. It's always from one tip. Make sure you stretch it over half, and then draw your arc. And then make sure when you pick it up, you keep it that same size. You don't want the size of that arc to change. That's the trick.
Okay.
And then move it to the other side. Swing another arc. Yeah. So it looks like maybe they're gonna be. I'm not sure. Somewhere, I think. But I mean, I'm pretty sure that's what he said. How to construct a circle there. Yeah. All right. What else, lady? Those are all the ones you circled. I glanced over some of the ones you didn't circle, but I focused mainly on the ones that you circle or you told me in the email that you were having problems on. That Cavalieres one, the scale factor. Radians looks like no problem for you. Radians, that volume scale factor one, that's a tricky one. Equilateral, that's a sucky formula. But sorry about that.
I think that's all the questions I had for this problem.
Okay. So your test is tomorrow?
Yes, tomorrow.
All right. Well, good luck. I hope you do good.
I have 60. That's something to help.
You're welcome. I hope it helped a little bit. And again, I'm sorry if this was my subject matter. I would be super professional. But
Okay.
I think I was able to figure out some of this to find those problems to help you out.
Mm-hmm.
So I hope that does. I hope you do good. All right. Well, look for this video.
Okay.
And good luck in all your sports, ladies.
Thank you.
All right. You're welcome. I'll talk to you later.
Bye.
Bye.